Georg Cantor, Georg Ferdinand Ludwig Philipp Cantor, was a German mathematician known for his groundbreaking contributions to set theory and our understanding of the infinite. And here is a brief biography of Georg Cantor. Early life and education. Georg Cantor was born on March 3, 1845, in St. Petersburg, Russia, to a family of Danish and Russian descent. His father was a successful merchant, and his mother was the daughter of a sculptor. Cantor showed an early aptitude for mathematics and began his education at the Realschule in Darmstadt, Germany. He later studied at the University of Zurich and the University of Berlin, where he was exposed to various branches of mathematics. Development of set theory. Cantor's most significant contributions came in the field of set theory, which he developed in the late 19th century. He introduced the concept of sets, set notation, and operations on sets, providing a rigorous foundation for discussing collections of mathematical objects. Countable and uncountable sets. Cantor is famous for his distinction between countable and uncountable sets, demonstrating that not all infinities are equal. He proved that the set of natural numbers is countable, countably infinite, while the set of real numbers is uncountable, uncountably infinite. Cardinality and transfinite numbers. Cantor developed the theory of cardinality to measure the size or number of elements in a set. He introduced transfinite numbers, including ordinal numbers, to describe the order or arrangement of elements in sets, and cardinal numbers to describe their size. The Aleph numbers, too, represent different sizes of infinite sets. Diagonal argument. Cantor famously used a diagonal argument to prove the uncountability of the real numbers, a pivotal result in set theory. This argument demonstrated that there are more real numbers than there are natural numbers. Challenges and controversy. Cantor's work on the infinite faced resistance and controversy within the mathematical community during his lifetime. Some prominent mathematicians, like Henri Poincaré, were initially skeptical of Cantor's ideas about the infinite. Later life. Despite the controversies, Cantor continued to develop and refine his ideas on set theory. He held various academic positions during his career, including teaching at the University of Halle. Cantor suffered from bouts of depression and spent time in sanatoriums for treatment.
Legacy. Georg Cantor's work laid the foundation for modern set theory and had a profound impact on various branches of mathematics, including topology, mathematical logic, and the development of axiomatic set theory. His contributions to the understanding of the infinite continue to be celebrated and studied in mathematics today.
Georg Cantor passed away on January 6, 1918, in Halle, Germany. Despite the challenges he faced during his lifetime, his ideas and discoveries have left an indelible mark on the field of mathematics. Georg Cantor is widely recognized as the founder of set theory. He made significant contributions to the development of set theory in the late 19th and early 20th centuries. Cantor's work on set theory revolutionized our understanding of the infinite and had a profound impact on mathematics as a whole. Cantor's key contributions to set theory include introduction of set notation. Cantor introduced the concept of a set and developed a notation to represent sets. He used set notation to describe collections of objects and their properties. Countable and uncountable sets. Cantor made the important distinction between countable and uncountable sets. He showed that there are different sizes of infinity and proved that the set of real numbers is uncountable, which was a groundbreaking result. Cardinal numbers. Cantor introduced the concept of cardinality to measure the size or number of elements in a set. He developed the theory of cardinal numbers, which includes the notion of Aleph numbers, too, to describe the cardinality of infinite sets. Diagonal argument. Cantor famously used a diagonal argument to prove that the set of real numbers is uncountable. This argument is a fundamental result in set theory. Cantor's theorem. Cantor's theorem states that for any set A, the cardinality of the power set, the set of all subsets, of A is strictly greater than the cardinality of A. This result has profound implications for the hierarchy of infinite cardinal numbers. Cantor's work in set theory sparked significant debate and controversy during his lifetime, with some mathematicians initially resistant to his ideas about the infinite. However, his contributions laid the foundation for modern set theory and had a lasting impact on various branches of mathematics, including topology and mathematical logic. The term transfinite and the concept of transfinite numbers were introduced and coined by the German mathematician Georg Cantor. Cantor's work on transfinite numbers was a significant contribution to the development of set theory and our understanding of infinite sets. Cantor introduced the concept of transfinite numbers in the late 19th century to describe and classify different sizes of infinity. He used ordinal numbers to represent the order or arrangement of elements in sets, and he introduced the term transfinite to convey the idea of numbers beyond the finite, extending to infinite quantities. Cantor's transfinite numbers are divided into two main types: ordinals. These represent the order or position of elements within a well-ordered set. The smallest transfinite ordinal is denoted as omega, and Cantor introduced various other transfinite ordinals, such as omega plus 1, omega plus 2, and so on, to describe different levels of infinity. Cardinals, these represent the size or cardinality of sets. The smallest transfinite cardinal is denoted as Aleph null, and it represents the cardinality of the set of natural numbers. Cantor also introduced larger transfinite cardinals, such as 2, and so forth, to describe larger infinite sets. Cantor's work on transfinite numbers and set theory led to a deeper understanding of the infinite and its various levels and sizes. It also played a crucial role in the development of modern set theory and mathematical logic. His introduction of the term transfinite and the formalization of transfinite numbers have had a lasting impact on mathematics and continue to be essential concepts in set theory and related fields.
A trigonometric series is a mathematical series that represents a function as an infinite sum of trigonometric functions, typically sine and cosine functions. These series play a crucial role in various areas of mathematics, physics, and engineering. The most famous example of a trigonometric series is the Fourier series, named after the French mathematician Jean-Baptiste Joseph Fourier.
The Fourier series expresses a periodic function as a sum of sines and cosines with different frequencies and amplitudes. It is particularly useful for analyzing and approximating periodic functions and solving differential equations with periodic boundary conditions.
The general form of a Fourier series for a periodic function f(x) with period 2 pi is given by.
Here, these coefficients are determined by integrating the product of the function and the trigonometric basis functions, sine and cosine, over one period.
Trigonometric series are widely used in various fields, including 1. Signal processing. Fourier series are essential for analyzing and processing signals, such as audio, images, and data. 2. Electrical engineering. They are used in the analysis of alternating current, AC, circuits and electrical waveforms. 3. Quantum mechanics. Trigonometric series play a role in the mathematical description of quantum states and wave functions.
4. Vibrations and oscillations. They are used to describe the behavior of mechanical systems, musical instruments, and other oscillatory phenomena. 5. Heat conduction. Fourier series are applied to solve heat conduction problems and describe temperature distributions in materials. 6. Partial differential equations. Trigonometric series are useful for solving partial differential equations with periodic boundary conditions.
In summary, trigonometric series, particularly the Fourier series, are powerful mathematical tools for representing and analyzing periodic functions and have widespread applications in science and engineering.